Hello everyone, welcome back to ACE Exams. This is Maath Alabdali and today I'll be explaining interference for A-level physics. Okay, so I'm going to cover these points in today's video. So I'm going to state the principle of superposition and I'll explain it. I'll apply graphical methods to illustrate the principle of superposition. I'll also explain the term interference, coherence, and path difference and phase difference, and I'll also state what is meant by constructive interference, destructive. I'll describe experiments and demonstrate two-source interference using sound, light waves, and microwaves, and I'll describe constructive interference, destructive interference in terms of path difference, phase difference. I'll describe the Young's double slit experiment, and I'll explain how it is a classical conformation of the wave nature of light. I'll use the equation lambda equal to ax over d for electromagnetic waves. I'll describe the experiment to determine the wavelength of monochromic light using laser and a double slit. I'll describe the use of diffraction grating and determine the wavelength of light. I'll state and use the equation d equal to sine theta d sine theta equal to n lambda, which is the diffraction grating. And I'll explain the advantages of using multiple slits in an experiment to find the wavelength of light. Okay, superposition of waves. So basically, the principle of superposition states that when two or more waves meet at a point, the resultant displacement is always equal to the sum of the displacement of the individual wave. So for example, in here you have a wave, okay, and if you look at point y, okay, and you got wave A, wave B, and then this is the resultant wave C. If you look at wave A, yeah, it's 0.7. If you look at wave B, yeah, it's 1.3. So if you add these two together, you'll get 2. No, yeah, if you add these two together, you'll get 2. So, and then if you look in here, y, it is 2, the resultant wave of C, which is 2. Similarly, if you look at Z, wave A is 1, wave B is 2, and the resultant wave is 3. So, yeah, that's basically superposition. Interference. So interference is, okay, so basically in here, two loudspeakers, they are connected to a single signal generator as shown in the diagram. So this is the diagram, yeah. The sound waves emitted by each speaker, so in here, they are of equal frequency, of equal wavelength and amplitude, and an interference effect will be formed due to the superposition of sound waves, and this is observed in the region in front of the speaker. So yeah, here. And at some point the waves, they arrive in phase with each other, and if they arrive in phase with each other, then the resultant wave is going to have twice the amplitude of each wave, and this is a condition where a loud sound is heard. And if you like, a quiet sound is heard is when wave A is in antiphase to wave 2, so or wave B. Okay, so in here the it's gonna have a 0 or very small amplitude, and a very quiet sound will be heard. And this is used in soundproof headphones. So you know, like when you buy really expensive headphones, they come like soundproof, so when you put them on, you cannot hear the surrounding. And this, the science behind it is when the wave is the wave from the surrounding and the wave like from the headphone is going to be in antiphase, and a 0 amplitude will be produced. And there are points in between the waves, so they are somewhere in phase and in antiphase. And so when there is this specific type of condition, then the sound will be somewhere between a very loud sound and a very quiet sound. And yeah, it's basically it. So interference are two types. There's constructive interference and destructive interference. And constructive interference is when the waves, they arrive in phase. So the example, when a very loud sound is heard, that is constructive interference. And in constructive interference, the waves, they are separated by distance of lambda, yeah. whole number of lambda, yeah. And in destructive, they are separated by odd numbers of half lambda. Um, so yeah, in destructive and antiphase, they give a 0 amplitude, and in constructive, they give a larger amplitude. That's basically it. In water waves, the interference of water waves can be observed using a ripple tank. And if you see in this diagram, two ball-ended diapers are made to vibrate underwater, and they're going to produce waves of the same frequency and amplitude. And this is basically the pattern that will be produced, and I'm going to look at this. So in here, there are regions where the waves are in phase. So for example, region X. So this is where the points are in phase, the constructive interference. And in here, larger amplitude wave, larger amplitude wave will be formed. Basically, it's just one wave X. And then at Y, it is destructive interference, because the waves are in antiphase. So there's one from here and then there's one from here. So the green and then the red, if you can look at the diagram. And over here it's destructive interference, and at X it's constructive interference. Microwaves. So microwave transmitter is microwave transmitter is directed towards the double gap in the metal barrier, as shown in the photo opposite, and the wave diffract through two gaps into the region beyond the barrier, where they superpose and produce interference effects. And a microwave receiver connected to a micrometer is moved along a line XX parallel to the metal barrier, and as the receiver is moved, the meter registers high readings as it passes through the regions where constructive interference is occurring, and low readings where destructive interference is occurring. So yeah. And if the receiver is at a point which gives a low meter reading and one of the gaps in the barrier is closed, the meter reading will increase, showing that the low reading is due to destructive interference of the microwave. So yeah, that's basically this. And then you have to memorize this. Yeah, you have to understand it really well and memorize it. You have to understand it in order to memorize it. You cannot memorize stuff when you don't understand it. You forget it next day. Anyway, light waves. So this is basically when a beam of laser light is directed onto a double slit. Okay, and then once it directs into a double slit, an interference pattern of equally spaced light dots is seen on the screen. So in here. And then the light dots, they're called interference fringes, and there's going to be there are points where the light waves are arriving in phase with each other to give constructive, and there are points where they arrive in antiphase, so destructive interference. So yeah. Explaining interference fringes. So if you look at point L first, okay, this is bright fringe and dark fringe. I explained in the previous slide that they produce interference fringes. So interference fringes can be bright fringe or dark fringe, and at point L, it's a bright fringe because it is constructive interference, and it's directly in the middle between S1 and S2. If you draw a line in here, it's going to be equidistant. So the path difference between the light wave from S1 and S2 is 0. Okay, and then this means that the waves are in phase with each other when they leave S1 and S2, and since they are in phase, it's going to be constructive interference, and a bright fringe is formed at L. At M, however, it's dark fringe because it's destructive interference, and I explained previously that in destructive interference, though, phase difference, they are separated by a distance of half lambda, and in here the waves from S1 and S2 then antiphase, and a dark fringe is formed. Okay, that's basically point M, and then point N is bright fringe again because it's gonna be exactly one wavelength, so it's constructive interference. So one wavelength and one lambda is the phase difference. No, it's the path difference. Phase difference is in degrees. So yeah, constructive interference, bright fringe, and that's basically it. So the double slit equation. It's really easy. You just have to remember that it's lambda divided by a equals to x over d, and then you rearrange it to make it lambda equal to a x over d. And basically, lambda is the wavelength, you know that, the wavelength of light. A is the slit separation, which is the distance between S1 and S2. So this is basically A. X is the fringe width, so this is X, and D is the slit screen's distance. So this is D. And then in the exam they'll give you numbers, and you just plot it in to get whatever you want to do. Rearrange it, get what the question asks you to do. But it's really important that you know the difference between A, X, D, and lambda is easy. Lambda is just wavelength. A is the slit separation, X is the fringe width, which is this, and D is the slit screen distance. So A, D, X. So coherent sources. So for interference effects to be observable, the interference pattern must be steady. So they must not change with time. This only happens if the wave sources they are in phase, or if they have a constant phase difference. Such wave sources are said to be coherent. So two waves are said to be coherent if the waves emitted from them are in phase, or if they have constant phase difference. If they are constant phase difference or they are in phase, they are said to be coherent. This implies that the sources have the same frequency. So, coherence happens when the vibrating dippers on a ripple tank are in phase because they are driven by the same source. Or, in case of microwave interference, the two slits emit waves derived from the same source, and the laser light is also coherent. So, in the exam, they might ask what the condition for observable interference. One of them is that coherent wave sources, which means they must have the same frequency, otherwise the interference pattern will be continually changing, and the interference wave should be of the same amplitude. So, to ensure good contrast between bright and dark fringe. Yeah. So this is the Young double slit experiment. So this has been provided by Thomas Young, which he demonstrated interference of light in 1801. And the diagram for more modern version of his apparatus is shown opposite. So basically, this is a sodium lamp. It acts as a monochromatic, which is a single wavelength light source, and it illuminates the narrow slit S. And diffraction at S causes diverging beam of light waves to fall on two narrow slits with S1 and S2, so this one and here, which are very close together and parallel to S. So this is it's parallel to that, and S1 is very close to S2. And since they are derived from a single source, since like the light is from a single source, the two slit act as a coherent light sources, and the diffracted light beam emerging from S1 and S2 overlap in the region beyond the slit, and superposition of light waves produce an interference pattern of bright and dark fringes in here. So bright fringes and dark fringes, and this can be seen on a wide screen from 1 to 2 meters from the double slit. So from this to this, it's just like 1 meter, 2 meter, 1 to 2 meter. Now, one thing you have to know is that the slits need to be extremely narrow, and as a result, very little light is transmitted. So the interference pattern is very faint and can only be seen in a darkened room. And a traveling microscope can be used instead of the screen. This makes the pattern easier to observe. And the modern version of this apparatus uses a laser light instead of a sodium lamp, which coherent light is shown directly at the double slit, producing an interference pattern which is bright enough to be viewed in daylight. Yeah, easy. Now, I mentioned earlier that the Young double slit experiment, that he basically confirmed that the wave theory of light, because the interference pattern could only be explained in terms of superposition of light waves from the two slits. So the bright fringes were explained by stating that such points the light waves arrive in phase, so reinforce each other, it's constructive interference, and at points where light wave arrive in anti-phase, cancellation occurs, so destructive interference and dark fringes. So if one of the slit is covered, the interference fringes disappear and the screen is then uniformly illuminated. This shows that the interference pattern is produced as a result of superposition between light wave coming from both slits. Yeah, that's basically the evidence of wave theory of light. Now, diffraction grating. Diffraction grating, it consists of a small glass plate with a very large number of closely spaced parallel lines scratched onto it. And when a beam of monochromatic light is directed at a diffraction grating, it passes through the clear spaces between the lines and it is transmitted in certain clearly defined directions only. So they're only transmitted in specific direction, which are the orders in here. I'll explain this. This is because as they pass through the slit, the light waves are diffracted, and those from adjacent slits interfere constructively in certain direction, which we call maxima, and destructively is minima. And the diffraction imaging observed include a zero order image, which is along the straight through which is along the straight through position, with the further images on either side, which are referred to as first order, second order, third order, and so on. Yeah, so basically a laser light through a diffraction grating gets diffracted and then many orders form. That's basically it. It's this. I don't think so you'll find this in the OCR textbook, but I found this I found that we need to know about diffraction grating in the specification, so you need to know about this. If we explain the diffraction grating, so this diagram, it shows a small section of a diffraction grating on which the monochromatic light of wavelength is normally incident. Consider what happens after the light passes through the grating. So in direction 0, it's the light wave which has passed perpendicularly through the grating, and the path difference between the light waves from adjacent slit is 0, and so they're in phase. And they're in phase with each other, and constructive interference occurs, and these light waves, they give a zero order maximum. So this is 0. Direction 1, which is this, it's basically when the when the path difference is 1 lambda, and the in phase and constructive interference occurs, and this is basically the first order maxima. And direction 2 is the second order maxima, and a path difference is 2 lambda, and so they are in phase and constructive interference occurs at another angle, and to the another angle to the central zero order maxima, and further maxima can be observed on either side of the central maxima for values theta up to a maximum of 90. So yeah, it can only happen up to a maximum of 90 because it cannot go back. So minima are observed between the maximum position, and in these cases the light waves from adjacent slits have to have a path difference of n minus half lambda, so where n is 1, 2, 3, 4, etc. This is destructive interference. So I explained earlier, destructive interference, the path difference is separated by a distance of half lambda. That's why it is destructive interference, not constructive interference. Constructive interference, 1 lambda, 2 lambda, 3 lambda. Destructive interference, half lambda, 3 over 2 lambda, etc. So the equation of the diffraction grating is n sine theta equal to n lambda, and theta is basically the angle, so in here, and the light waves traveling along direction 1 interfere constructively to give first order maxima. For this to happen, the path difference for light waves from adjacent slit is 1 lambda, and yeah. So the use of diffraction grating is used to measure the light wavelength. So a monochromatic beam of light is directed at the diffraction grating of non-grating spacing d, and diffraction angles theta 1, theta 2, theta 3, etc. for the first, second, third order, and yeah, and then the results are given in the equation d sine theta equal to n lambda. This is used to determine the wavelength of light. Now, the advantage of using a multiple slit is to make it more clear. So if it's with a double slit, it's going to be faint unless a laser is used, or blood, so they don't have a definite image. This makes it difficult to measure the fringe width accurately. So we use multiple slits to make a much brighter maxima and a very sharp maxima. Okay, thank you for listening. See you in the next video. Stay safe. Make sure to subscribe. We're trying to reach to 100 subscribers. Thank you very much for 100 subscribers, and see you in the next video. Bye bye.